Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 2. Examples of numerical differentiation. In this first example, we consider the following explicit function, which is continuous and differentiable at x equals 1. Find the first derivative at x equals 1 using the forward and central difference formulas with h equals 10 to the minus 1, 10 to the minus 2, down to 10 to the minus 7. The true derivative turns out to be long, involving complicated expressions. For x equals 1, the first derivative is pi over 4. We will use the forward difference formula, which is a first-order approximation, and the central difference formula, which is a second-order approximation. We will tabulate the approximations with both formulas along with the true errors. For h equals 10 to the minus 1, the forward difference formula yields the true absolute error of 2.533 times 10 to the minus 2. While the central difference formula results in the true absolute error of 2.758 times 10 to the minus 3. For h equals 10 to the minus 2, the forward difference formula leads to the true absolute error of 2.287 times 10 to the minus 3, while the central difference formula yields the true error of 2.748 times 10 to the minus 5. For h equals 10 to the minus 3, the forward difference formula leads to the true error of 2.263 times 10 to the minus 4, while the central difference formula yields the true error of 2.746 times 10 to the minus 7. Notice that when the value of h is reduced by 10 folds, the true error with the forward difference formula is also reduced by 10 folds, while the error with the central difference formula decreases by 100-fold. When the table is completed, we observe that this trend continues, which depicts the order of accuracy of the difference formulas. The truncation error for the forward difference formula is about 0.226 times h. For the central difference formula, it behaves as 0.275 times h squared. It should also be noted that the true error in the approximations with central difference formulas for h equals 10 to the minus 6 and 10 to the minus 7 display an increasing trend. This is an indication that round-off errors are becoming dominant. The second example problem involves calculating the first and second derivatives of a discrete function, which is generated from a known function, f(x). The reason for using a known function is to be able to calculate and assess the true errors. Note that the dataset is uniformly spaced with spacing of h equals 0.2. For I equals 0 or x equals 0, we will make use of the second-order forward difference formula since this data point is the left endpoint of the dataset. The forward difference formula for f0' involving f0, f1, and f2 takes the following form. Substituting the numerical values, we find f'0 to be minus 1.04. We can use the central difference formulas for the interior data points, that is, for I equals 1 through 4. f1' leads to the following formula. Substituting f0 and f2, we get 1.92. Similarly, f2' contains f1 and f3. Upon substituting f1 and f3, we get 6.8. f3 prime involves f2 and f4, which gives 16. f4 prime leads to f3 and f5. Upon substituting f3 and f5, we find 30.48. For I equals 5 or x equals 1, we will make use of the second-order backward difference formula since it is the right endpoint of the dataset. The backward difference formula takes the following form. Substituting the numerical values of f3, f4, and f5, we obtain 47.84. Now, we turn our attention to calculating the second derivatives. For I equals 0 or x equals 0, again, we use the following second-order forward difference formula, which makes use of f0, f1, f2, and f3. Substituting their numerical values, we find f double prime 0 to be minus 4.4. For the data points from I equals 1 to 4, i.e., the interior data points, we can employ the central difference formula, which uses the central point I and the data points to its left and right. For I equals 1, substituting the numerical values of f0, f1, and f2, we find f double prime 1 to be 14.8. For I equals 2, the difference formula contains f1, f2, and f3. Substituting their numerical values, we obtain f double prime 2 as 34. For I equals 3, the f double prime 3 involves f2, f3, and f4, which gives 58. For I equals 4, the f double prime 4 involves f3, f4, and f5. Upon substituting the numerical values, we find 86.8. Finally, for I equals 5, we use the second-order backward difference formula, which results in 115.6. Note that the true errors for the computed derivatives are provided in the last two columns of the tabulated results. The truncation error for the first derivative involves the third derivative of fx, which is 120 xi plus 60. Its maximum value occurs at xi equals 1, which is 180, in which case, the maximum magnitude truncation error becomes 1.2. We note that for the interior points, the true errors are in fact less than 1.2. We leave it to you to find the truncation error for the endpoints. On the other hand, the truncation error for the second derivative involves the fourth derivative, which is 120. It is independent of xi. This implies that the truncation error will be constant regardless of xi. Calculating the truncation error, we find it to be 0.4, which is the same as the true errors tabulated for the interior points in the table. The largest errors are observed to occur at the endpoints of the dataset. The forward and backward difference formulas use the nearest three data points and a quadratic function to approximate the curve. The plot of fx is shown. We note that the function has a saddle point at x equals 0. Forward, backward, and central differences approximate derivatives by using values of the function at nearby points. The numerical differentiation error is influenced by the curvature of the function. If a function has high curvature or sharp changes, the approximation error increases where dramatic changes are observed. This is because numerical methods assume the function behaves approximately linearly or quadratically over the small interval between points. For highly curved functions or near inflection points, this assumption can yield less accurate results. The error at the left data point implies that the function is decreasing, whereas as can be seen from the data, the function is increasing. That is because the approximating polynomial at left endpoint is a parabola, which decreases down to the local minimum point at about x equals 0.07. A 3-point formula in this case is not sufficient to predict the curvature at x equals 0. Higher derivatives can also be numerically calculated by successive differentiations. F double prime equals derivative of f prime, f triple prime equals double prime of f prime, etc. This approach causes the uncertainties already present in the original data, as well as the total errors in the computed quantities, to be propagated to the next level. In this regard, a prudent approach would be to use the original discrete data set with the suitable finite difference formulas of the desired order of accuracy. That is all for now. See you next time with another topic. Bye.